Good morning to everyone joining us for another webinar from MEGGER webinar series. My name is Sazan Adnan and I'll be the moderator for the session today to support you with your questions and technical issues. Please feel free to write in the chat anything that you may want help with. Today's webinar will be a pre-recorded session about understanding proactive cable maintenance programs and testing behind them. The topic is pretty much explanatory, and we will talk about all cable maintenance programs and why do we do these tests. Panelists joining me today for this session is Mr. Mohammed Haiki, who is a cable segment manager in MEGGER Middle East. He'll be answering the questions after the session has ended. So before I start the recording, I would like to highlight a few things. You're all been muted to avoid any disturbance during the presentation. You may ask any question during the presentation and we will answer after the presentation has ended. By the end of the session, if you would like to ask the panelists any questions, you may use the raise hand feature and we can open your mic. You can ask your questions in both Arabic and English and we will answer it. Please note that the recording will be sent within the next 2 days within the WebEx system as a standard procedure. Also, you may request product demo, product quote, or just an attendance certificate by answering the survey questions that's going to appear after the session has ended. So any requests that you have, whether it's regarding a product, a certain product, or attendance certificate, or anything, a technical question that we didn't answer during the session, you may use the survey question that will appear at the end of this webinar to request the same. So as I mentioned before, you can use the chat box to highlight any problems that you might have with the connection, or also you can ask any questions and we will answer after the session has ended. And this is how the survey questions is going to appear after you close the window, the WebEx window, once the session has ended. Also, if you are interested in more MEGGER webinars, please visit us at www.megger.com/webinars. And I would recommend you to follow us on social media accounts, Facebook and LinkedIn, to get all new updates about products and webinars. If you have more questions, please email us on memarketing@megger.com or just write it in the survey questions. I will now start the recording. Please let me know if you can view the recording.
Talking today on understanding proactive cable maintenance programs and the testing behind them. But we're going to get into a lot of different topics here. We're not just going to think about cable testing and the technology behind what identifies cable failure modes. We're going to think about cable life and performance to extend the cable asset life. And this is going to be presented by myself and Charles Nybeck, my colleague. So without further ado, the agenda is going to be cable asset performance management. We're going to get into some failure mechanisms within medium voltage cables. We're going to talk about the test and diagnostic tools to detect those failures, what service types that we offer, what to expect, and then we'll get into some frequently asked questions as well. So, as I said, this is not just about testing cables. This is about making decisions on those assets for our customers and our partners. So it's going to be those beginning of life issues, those commissioning. Let's talk about, say, wind farms or solar or new feeder commissioning. Being able to predict end of life, so decision-making process to repair or replace or just to simply leave in the ground as like new cables, and really get into useful asset life to maximize asset return, if you will. So what we're trying to do here is give our customers insight into their cable systems. If you think about underground systems, they're generally hard to evaluate. They're not like overhead where you can actually look at the condition. These are hard to evaluate just because of their inherent concealment. And really, even if we had all the money available to us to replace aging systems, we don't have the human resources to do that job necessarily. So we're going to look at technology solutions to deal with these assets. So we're going to give you insight into the cables, into your cable systems. Basically to identify those components of the cable system that are healthy. So when we think cable system, we think the terminations, we think splices, and we think the cable itself. We're going to be able to tell you what of those components could be repaired, what system should be replaced based on how severe the issues are, and really more importantly, when these components should be rehabilitated, maybe using some rudimentary risk of failure modeling, just to get to the benefits to optimize resources. As I said, that could be human resources, it could be just project time to complete a project. We want to improve reliability, so bring the reliability indices to manageable levels. So whatever key performance indicators that you're looking at, whether it's customer minutes of interruption or safety or KFI, to bring those in line to where they're manageable. We want to help you reduce your O&M spend, so you have less unplanned outages, which is of course going to reduce O&M expenses. And we want to show you how you're going to increase capital reach. Since some cables are going to assess as defect free or as good as new, then we're able to increase asset return or capital reach, and we'll get into that. So what I'm going to do right now is hand it over to Charles Nybeck, my colleague, who's going to talk about failure mechanisms in medium voltage cables and those tools to test and diagnose those cable systems. So Charles, I'm going to hand it over to you right now. Thanks, Charles.
Thank you very much, Darren. I appreciate the introduction. And thank you, everybody, for joining us today. Hope you're having a good day. So as Darren had mentioned, you know, medium voltage cables are suspect to damage, defects, and issues that can be inherent from several different incidences. And first, we're going to take a look at some local issues that can be found in either the joint or the termination. So if we look into those issues, we can see that these are typically going to be workmanship issues. And the reason being is, if you think about it, the person that installs these splices, these joints, or these terminations are people. And although they didn't mean to, sometimes people accidentally make mistakes. That could be uneven cutbacks, that could be sanding wrong. So there can be some mistakes that are made, cuts into the insulation, what have you. And although they seem small at the time, when in service and over a period of time of aging and deterioration, they can lead to a failure. If we look at the termination, we can see a failure in the termination. And if we look at the splice or the joint over here, we can also see some obvious tracking, discharges, and ultimately some defect there as well. Next is another local issue, but this is weak spots in the actual installation of the cable. And there's several different reasons for this as well. One could be manufacturer defects, which over time can lead to electrical trees within your cable, which we all know is it's a very bad defect to have. So, we want to make sure that we check for those. Another one is a small bending radius. So these medium voltage cables have a rated bending radius. If you exceed that bending radius, you could damage that cable permanently. It could have an inhomogeneous field distribution then at that point, and can cause some field concentrations, and then therefore some defects, maybe even some partial discharge at that point. So we really want to make sure that we avoid these local weak spots in the insulation as well. Lastly, we have the insulation global issue. Now, by global, we mean all-encompassing, like the whole cable. So this is an integral measurement, and I'll get into this a little bit more on a later slide. But this global issue can be things such as water tree ingress due to just kind of natural aging, or subject to moisture, as well as the cellulose degradation within the insulation as well. Here we wanted to take an example to look at some specific local problems that we found, where first we have an example of a transmission cable here. I know the focus is medium voltage cable, and we'll get right back to it, but I just wanted to show an example of a defect or some damage that could be done by installation or through transportation. Now next, we do have a medium voltage cable here where you can see that we have a heat shrink splice, and that splice wasn't heated all the way to be totally uniform or connected to the cable there, the insulation there. And if we look, we can actually see resulted tracking, and you can see that the cavity that's created there, partial discharge activity taking place, and you can actually see that tracking on the cable itself there, that insulation. Next is a example of clamping a cable. So you just have a cable clamp to hold the cable in place. Now these are supposed to be specified to a certain torque. You shouldn't over torque these to cause damage. Now in this case, what had happened was that there was too much force put on these and ended up causing damage to the cable. If we look, we can see all three cables were over torqued and therefore permanently damaging the cables. And similar to the bed radius, what that's going to do is it can affect the field, the electrical field distribution at that point, and again is a prime point to have some partial discharges or other defects taking place. And that's going to be kind of in the main insulation, obviously, between any of your splices or terminations there. Finally, we have an example of what happens whenever these defects are not really, there's not action taken on these defects. As we mentioned before, these defects, they start out as defects, right? But over time, they can lead to a failure. And in this case, at the termination of this cable, we can see a failure. It's the result is that there's ash blown all over the side of the building there. So catastrophic failure there, as well as in this next example here, we can see another severe failure as well. And the issue is with these is not only do you have to replace what was damaged, but you also have to deal with the cost of an unscheduled outage in this case as well. So the question is what can we do to stop these defects or determine that there's defects and then take corrective action so that way we don't get those failures, right? So here we have a list of 3 test and diagnostic tools that can be used to do exactly that. The first is VLF, or very low frequency. VLF is a simple, non-destructive withstand test that can be performed. So similar to a high pot, only performed at 0.1 hertz and non-destructive. And the beauty of this test is it provides a very clear pass or fail result where there's not any need for interpretation. What I mean is if you perform a VLF test and you pass, you apply your VLF withstand for 30 or 60 minutes, and if you pass, you have no failure. Right? So it's very clear. Now, if you do have a failure, it's going to tell you you're essentially driving a defect in that cable to failure, and therefore the test will indicate that you have a failure. Now, this sounds negative. It sounds bad, right? Because you failed the cable. But if you really stop and think about it, you took a defect that was close to failure, and during a planned outage and testing, you drove it to a failure, and now you have the means to locate the fault through some fault location equipment, make the repair, and then put the cable back in service, back close to that like new condition, with the peace of mind that defect that was close to failure is now identified and repaired. Now, another valuable tool is tan delta here. And tan delta is a measurement into the cable's insulation or dielectric strength. This is an integral measurement, and what that means is it's a global measurement. So if we think back to the failure mechanism slide and we think of the global issues, this is a measurement that will help us to understand if there's the presence of water trees or cellulose degradation, and give us really the overall condition assessment of that cable insulation. And through the IEEE 400.2, we can actually get immediate field results as to whether or not there needs to be action to take, action required or no action required, or even further study into the cable. And tan delta is a non-destructive measurement, won't stress your cable. So once the cable is confirmed to pass or has a confirmed good measurement, the cable can be put back in service and with peace of mind. Now, the last one we have here is partial discharge. And partial discharge gives you the ability to detect developing defects before they occur. What that means is you have a chance to find defects at an earlier stage, right? So before they become a real issue or lead to a fault. Also, partial discharge is often used to verify workmanship issues. So if you had splices or terminations that were redone on a cable, partial discharge testing is a good test to do to verify that that was done correctly. Now, partial discharge can also identify or testing for partial discharge can identify whether or not you have PD activity that's occurring while the cable's in service. And the way you do this is determining the PD IV and the PD EV, which is the partial discharge inception voltage and partial discharge extinction voltage, respectively. And I'm not going to get into great detail, but the thing is if both of those values, the PD IV and EV, are above your operating voltage, then you can have good peace of mind that you're not going to have partial discharge activity while the cable's in service. And there's more than just the black and white case, but this is more or less the case. And if you have your partial discharge inception and extinction voltage below the operating voltage, this is a completely different story. That means that despite the situation, you're going to have partial discharge taking place within that cable, and it's eventually going to lead to a failure. Also, if you have an experience analysis of your partial discharge testing, you can use this as the basis for your further assertive decisions. So again, really the three test and diagnostic tools that are strong for determining the condition of your cable here. Next, we'll take a look at the service types that can be provided by using these three test and diagnostic tools. And this can cover commissioning, acceptance, or maintenance testing. If we look at the far left picture, we can see we have the complete picture by using the three tests, the VLF, tan delta, and PD. That means we can find the global assessment of the cable so we can determine the overall health of the installation. We can run partial discharge tests to determine if there's any issues within our accessories, our splices, or our joints or terminations, and if there's any weak spots identified. And then with VLF, we can drive those weak spots to a failure. We can repair them, and then you have the complete picture, and you have all things on the table to perform any service or any repairs that you want to do. Next, in the middle, we have the condition assessment of service age cable, which you can notice involves PD and tan delta, and we're missing the VLF. So in this case, we have tan delta, which gives us the global or overall assessment into the condition of the cable. And we have partial discharge testing that allows us to assess the accessories such as the joints, splices, and terminations, as well as maybe even find some of the weak spots in the cable. You really kind of want to shy away from VLF in this situation because it's service stage cable, and you don't really want to add unwanted stress to the cable if not necessary. Now, in the terms of the right, we have the commission and acceptance testing, which involves partial discharge and VLF, and you'll notice tan delta is missing. And the fact is that through partial discharge, again, you can verify the accessories. Through VLF, you can determine that there were no gross defects during the manufacturing process that may lead to a failure. Tan delta is not really recommended in this case because the cable still has some of the chemical processes taking place that are going to influence that dielectric measurement and won't really be a representative tan delta measurement. So you really want to wait some time while that cable is in service to let those processes take place, settle, before you perform your tan delta measurement, as if you performed it on a commission test, it really provides no value in trending or any measurement moving forward. Now, if we start to take a look at these individually, we can take a look at the complete picture here. And as I had mentioned earlier, with the complete picture with PD, tan delta, and VLF, we have the ability to not only determine the global condition of the cable insulation, but we can now look at the joints and terminations through partial discharge, as well as weak spots. And then with VLF, we can drive any of those weak spots that are close to failure, and then have the chance to do those repairs while in that outage, that planned outage, as you don't have the failure or the defect driven to a failure while in service, causing an unplanned outage. If we look at the condition assessment of service age cable, again, kind of just visually showing what I said earlier, we can determine the global condition assessment of the insulation of the cable, and as well as still with the partial discharge, we can determine the condition of the joints, splices, and terminations to determine that there were no workmanship errors that may lead to a defect in the future. Now you can see the weak spot is X'd out, but in reality, we can find mid-span PD activity in the insulation joints or splices or terminations. And one situation may be similar to, and I'll call upon this again because we're going to kind of look at a measurement example that could show something similar, but it could be the over clamping of those cables or the bend radius exceeding that bend radius. So that could be a situation where you may find midspan PD and find a local weak spot. Then we have our commission acceptance testing. So again, through partial discharge testing, we're able to find any issues, workmanship issues in our joints, splices, or our terminations, as well as any localized weak spots in the installation that may be due to the manufacturing defects or the way it was handled. Now, since we don't have tan delta being performed here, we don't really get the global assessment of the installation condition. But if you think about it, from the manufacturing process, there shouldn't be any cellulose degradation. Should be no water trees if it was handled and transported correctly. So that tan delta measurement, again, is not really going to be consequential in this case. Now here we have an example of the PD detector software. And so really what I wanted to do here was just kind of step you through the software for doing a partial discharge measurement, just kind of give you a visualization of what may happen. Where here we have the home screen, if you will, of the PD detector software with the library up top, where you can have your cable number, the location of the cable, your station A and B, so near end and far end, and you can swap those so you don't have to rebuild the cable later. The length and meters, as well as your RMS voltage, so you can kind of see all of that, and that's all of your header information. If you move forward, you see you have the pinwheel, classic pinwheel design here, where it steps you through each process. But really, if we look, we can see we've built the cable, and that's the real thing. We have station A, we have about 1,020 meters of cable. You can see a splice indicated by the gray bars there, another stretch of cable with another splice, and then finally a small stretch of cable to station B. And here we have a classic example of a calibration of a cable. So here in this case, we're injecting 1 nanocoulomb. And that can be seen at the very bottom where you see the periodic spikes. Those are actually the injection of the calibration signal. And then that thick bar of black at the very bottom is actually the background noise. So you can see that it provides a very good signal to noise ratio there. And there's actually a screen past this, we don't show it, but it's the disturbance level where you can actually quantify the background noise. If we look at the top, you can actually see the calibration itself where we have a very strong signal on the near end. You can see the very first splice there. A little bit after, you can see the second splice, and then just after the second splice, you can see the nice reflection from the far end of the cable. So here we have an example of an actual partial discharge measurement using the damped AC or DAC waveform. So we have capability of performing partial discharge testing using several different waveforms, ranging from cosine rectangular to VLF sinus to damped AC. This is an example of a damped AC waveform. You can see at the very top as it decays over time. And at the very bottom, we can see that we have partial discharge measurements, but not only do we have the measurements, but we have them localized as well. So you can actually see lines 1 or phase 1 and 2 indicated by the blue triangle and the yellow or orange square respectively. We can see that the localization shows that that partial discharge activity is taking place at that splice, which is indicated by the dotted line at that 100-meter mark. So again, just kind of showing the fact that we can not only determine local, if we have PD activity, but also localize it to where in the cable are we actually seeing that. We also have another example here where we have several different sources of partial discharge. So we can see partial discharge at the splice in the middle, indicated at by phase 2. But if we look kind of to the right and left, we see some other, kind of mid-span PD activity. And that was what I was talking about earlier, finding partial discharge in the action, between the splices, which is in the very middle there and towards the right at about just over 900 meters there. So we can see that between those two, we have PD activity on phase 1, 2, and 3. And a situation like this, as I go right back to the cable clamping, is if those cables were clamped and over torqued, then you can cause inhomogeneous distribution of field and cause PD activity to take place. And it was done on all 3 phases. So this is something that could be representative of a condition like that, where you may cause a defect by over torquing your cable. This is the same measurement, but just shows the damped AC applied wave on the bottom. And those blue spikes you see coming up on the first waveform is, or the first period of the waveform, is actually the partial discharge taking place. So that's the partial discharge, then it takes it and it maps it and localizes it for you in the above graph there with the PD level and the distance at which the partial discharge is taking place. So again, just wanted to show an example of kind of what a partial discharge measurement would look like. So here is an example of what to expect with an in-depth consultation to determine the overall scope of your application, which in this case is a cable replacement project. And the measurement method in this case would likely be tan delta and partial discharge, in which the three-step process would be to first safely de-energize the cable. Second, we'd connect the tan delta unit and take our measurement. This is approximately 5 to 10 minutes here. And then third, we would do our field evaluation of the tan delta results, which we saw earlier is done by the instrument and gives us back whether or not action needs to be taken, no action can be taken, or further investigation. So if the cable passes, we can then perform partial discharge measurements and verify that the accessories for defects. So now that we know the overall condition of the cable is good, we can then look at the splices and terminations individually, determine if they need to be replaced or what have you. If the cable fails the tan delta, then we can simply move on because we already know that the overall condition assessment of that cable has failed. After the evaluation, we'll do our post-test evaluation and then generate our final report with our findings. So just a very simple process and to the cable replacement plan there. Here, just kind of wanted to show an example of kind of our test instrument and setup. Expediency is always an issue with this, so just kind of wanted to show you the simplicity, where in this case we have a TDM45 with the base module and boost module capable of performing tan delta, VLF, and PD with those three waveforms or wave shapes that I had mentioned, the damped AC, cosine rectangular, and VLF sinus. Where first connection that we need to make is just our ground connection, interconnecting the units into the station ground. Next is our control unit from the boost to the base module. And we have our input power. And then finally our high voltage that interconnects the two units and then to the cable under test. So you can see 4 connections, very straightforward. Now we're ready to perform both VLF and tan delta measurements. In the next case I wanted to show you is the TDM45 in the case of partial discharge. You can see that there's a few more accessories here, but once we step through, you'll really see how easy it is to set the. Again, our first connection is going to be our ground connection. Second will be our input power to both the unit as well as the communication box. Next, we have our comms from the unit and through the PC that controls our PD detector software that we saw on the previous slide. Next would be the trigger. That's for the boost module to the comms unit for our partial discharge measurement. And then you have communications to the PDS60, which is your partial discharge coupler. So that has your reference capacitor, your coupling capacitor, and your conditioning electronics. And then finally, last but not least, our high voltage cable leading to the PDS and then to the device under test. Unless the capacitance of the cable is low, and in which case we would add a support capacitor that would be between the test system and the PD coupler. So again, very straightforward, simple measurement, but what you may more likely see is actually the next case. And in this case, we have all of these into a compact test van. So now not only do you have the capability that we just showed you, but you have cable fault capability. So if you were to run a VLF, you could simply run your cable fault afterward. And this is all, again, in one compact design in a test van that's designed to do this. So you can see on the left, you have some cable fault equipment. You have your command center or your control center there. You can see the woman on the left that's controlling it with the classic pinwheel turn knob. It's touchscreen computer, runs on the Linux system. So again, fully complete to run all the tests. And if we actually look at the back of the van, we can actually see the TDM45 actually labeled there. You can see the high voltage cable being pulled out. You have your grounding cables, your communication cables. You even have on the bottom of the drawers there some accessories that come with the van as well. So that'll be including the diagnostic set as seen on the left here. And then some additional accessories, as well as some safety features such as a grounding rod to check the ground, the condition of your ground, as well as the status of the test and your e-stop. So again, you know, you may have just the simple TDM system, or you may have the full cable system that's capable of all of your test and diagnostics, as well as cable fault location and one convenient, unique, compact design there. So here we want to take an example to show you some field results and some memory, just kind of a classic example of a tan delta measurement. So this is kind of what I was talking about earlier as to the assessment of tan delta after the test is performed. We can see in accordance to the IEEE 400.2. And in this case, there was action required on all three phases, but there's three possibilities of no action required, further study advised, or action required. So you get immediate results and recommendations there. And the other thing is that the internal memory stores these measurements for your reporting. So while in on-site testing, that's all you need to focus on. You run your test, you move to the next test, you run your test. Afterward, we can pull all the data for our final reporting. And speaking of reporting, here's an example of some reports. On the left, we can see an example of a fault that's found at 220 meters. You can see that on the bottom on the cable diagram on phase 1. You can see at 220 meters we have a fault, so it actually indicates that for you. If we look at the top on the left, we have our header information. On the right, you actually have a geographical mapping of that cable with an actual, localized map, and shows you the defect there as well. So comprehensive reporting capabilities. And on the right, if we look and we see we have the analysis, so we have the charts, the measurement data, as well as recommended action. In this case, a tan delta measurement was performed. We can see at 9.4 kV, the frequency, the voltage steps, as well as the results of the measurement and some of the statistics that were determined there, as well as the result giving us the recommendation.
Well, thank you, Charles. I appreciate you explaining all of that. And I'm going to take over right now and get into the managed cable services part of the presentation, which is going to discuss the operations and the decision-making process. So just to start off here, I want to say that utilities are faced not only with aging assets, they also have an aging workforce. So we know that they need technology to help them manage and extend cable asset life. If we look at the United States alone, 6 million miles of power distribution systems and 18% are buried underground. And many of these assets are at the end of their life expectancies. So we know that utilities have difficult decisions to make, whether it's to just run to failure or it's replace complete loops based on age and failure rate. They're definitely dealing with deteriorating asset performance. So what we're going to show in this part of the presentation is some effective solutions to be proactive, to save money, to save time, and prevent basically power outages. And we already said at the beginning that even if the utilities had all the money, all the budget, they still don't necessarily have the resources to deal with their aging infrastructure. So it's going to take a technology approach. So what drives this? Basically, as we read about the utilities, grid hardening and modernization is at the forefront. We know there's government regulations in terms of the reliability indices and the key performance indicators around safety and KD and SAIDI, et cetera, customer minutes of interruption. So what we're looking to do is help our customers verify the integrity of their power systems to increase that reliability. And there's two ways you can do this. With new assets, we can offer cable commissioning and acceptance testing. And this is mostly project type work where we would maybe have help you verify the integrity of new feeders or the cables at a wind or solar farm, and certainly at critical facilities. And typically this is an insurance policy at the beginning of life for that cable, it's, as you get the defects out of a new system, it's going to have a major influence on asset lifetime performance, and it's going to help you maximize your investment return. Typically, these types of engagements are pretty low. In contrast, we also want to look at the other end of the continuum, which is a cable life extension program. And this is those age type assets. They've been in the ground for quite a while. In some cases, they could be at end of life. They've been fully depreciated. And basically, it's program type work, where based on your scope, and your scope could be, hey, we're having problems in our scope where 80% of our issues are coming from 20% of our installed base. So that could be, some older cables, pre-1985, for example, cables that are 35, 40 years old, fully depreciated. And reliability needs improving in this area. But this would be then an alternative to wholesale replacement. You're only going to rehabilitate those cables that are non-passing, that they don't pass the test. So this is more of a value-based opportunity, more than an insurance policy. This is going to help you just deal and make proactive decisions on, as I said, only those cables that have defects. So we're going to have a focus in these cases of reliability improvement. We're going to look at extending capital, and as I said, proactive replacement, reliability improvement is also going to reduce your O&M spend. So again, looking to avoid those unplanned outages and maximize asset return. In this type of engagement, if you have a scope of cable where, I've seen 10,000 miles falling into a scope of, pre-1985 cable, unjacketed cable, it depends on how many cable test bands you want to throw at it, the solution which we're going to help you, and we have calculators to do this that are online that I'll get into, but this is all going to be dependent on scope. This is not just about testing one cable, it's looking at testing whole populations of cables. So we'll get into that a little bit more. So what do you need from us as our prospects or our customers? You need high quality, you need reliability. So you need to be able to trust the results. So you need reliable asset condition analysis. You're going to need some form of consultation. So you're going to rely on maybe our expertise and advice on solutions in terms of newly installed systems and even what's going on with your aging systems. And it's got to be cost effective to optimize resources. That could be your capital resources and your human resources. So I look at this in terms of 4 pillars. What we want to do is choose the right technology. So we want to optimize the technology. So Charles touched upon it. We have the complete picture in terms of partial discharge, withstand, and tangent delta or tan delta testing. But the issue here is not just to be accurate. We have to be efficient and integrated into your systems. In other words, we could, if we're only testing one cable a day with a cable test van, then we're not efficient. So what we have to be is testing 5, 6 cables a day. So it's not just about choosing the right technology, it's also being accurate and efficient and integrated into your systems. So that's the second part, is system design and integration. So find a complete solution and integrate it into your OMS system, your outage management system, your GIS, or your asset management system, and maybe even possibly taking responsibility for the actual rehabilitation of those cables that don't pass the test, but certainly giving you some form of consultancy there. Offering innovative services to just apply the technology wherever you are, and even get into predictive life of the asset using artificial intelligence and machine learning, looking at margin of clearance of over operating voltage in terms of partial discharge, how severe is the issue, looking at phase patterns and using phase pattern recognition, but really coming up with these innovative services so that we can help you predict asset life, and then consulting with you, making sure that we're not just supplying you with the product, we're actually supplying you with asset and process consultancy. So even if there's people that are attending or companies that are attending this presentation right now, if you have our equipment, to come out and consult with you on that equipment. Maybe you're looking at starting a life extension program. We can send consultants out and work with you for a week or two or a month on how you might start up an asset management program. So that's something to bear in mind. And this slide is just basically showing asset life cycle. When should you test? Probably everybody on the call is familiar with the bathtub curve, which is in the lower right-hand side of the screen here, where it starts out at infant mortality. This is your start of commissioning, and then you have a period of useful life, and then your asset wears out. This is exactly the same with cable. At the end there, over time, you have a fully depreciated asset that's written off the books. So we can actually do quality control testing. This is that commissioning or acceptance testing, minimizing the risk of failure on new installs by identifying those craftsmanship issues, manufacturing defects. It could be shipping and handling, but basically looking to extend the life of that new asset. And then having regular maintenance throughout the useful life period, maximizing the cable system reliability and asset life by detecting and eradicating defects. And then extending the life with having a proactive asset management solution of medium voltage cables, where you can optimize capital investments and optimize reach of your budget to extend the life of those assets. And we're going to get into that as we move forward here. So what can you expect after the cable is de-energized? What we've done here is we want to show you just a loop here, and just for experience here, I'm just showing a loop here of 6 cables from riser to riser going through the neighborhood. And what you can expect here is, what we're going to do is we're going to set up with the van at the first transformer here, and we're going to conduct the first test from transformer to riser. We're going to identify any issues of terminations because they're above ground, and remediate any that have any discharge right there. So we're going to initially remediate any issues right away with any termination issues that we see. That's those local issues that Charles had mentioned in the first part of this presentation. And we're going to retest if that happens. While we're there, and if we're at the normal open point, we're going to check for arrestor protection and install it if needed. We're going to report transformer condition. That could be if we see a leaking bushing, for example, we're going to report it. If we see that the pad mount has subsided or it's crumbling, then we might as well report that. That's typical O&M maintenance, but why not report it right here, because we're at the asset anyway. So this is ancillary information, if you will. We're going to report then any mid-span defects or at an in the installation or within a splice. And if mid-span defects are found, then we're going to follow up with we're going to have you follow up with rehabilitation crews that will repair or replace that cable based on a risk of failure analysis. And then we're going to move to the next cable, as you see here. This time we're going transformer to transformer in assessment 2. Assessment 3 is transformer to transformer at the open point there, which could get moved, or you could take a full outage for the neighborhood. Assessment 4 is then, assessment 5 is then taken, assessment 6. So that's typically a day's worth of work in assessing cables with a cable test van. So let's look at this in terms of asset management solutions now. If we're the asset manager and we're looking to extend the life of our current system using this proactive approach, only dealing with those cables that have the defects. So again, using the same loop here, we're looking at the 6 cable segments. Just for example's sake here, I'm showing that each cable segment is approximately 350 feet long. So, and the replacement cost is about $100 per foot, which is not out of the realm of possibility, by the way, looking at an all-in cost of $100 per foot to replace cable. And this is why we say this is an expensive proposition. If those cables that are in the ground are passing these tests, then nothing more needs to be done to them. So you're basically, they're like new cables. Going back to the example here, we have the entire loop of 6 cables, 6 spans basically, times 350 feet, times $100 a foot replacement. That would $210,000 to replace this whole loop. So the asset right here, if we look at the loop as the asset, it's $210,000. And the reason why I like to look at the loop itself, because the loop really is as strong as its weakest link, or in this particular case, it's as strong as its weakest link in the half loop or the radial. So each cable span here is worth $35,000. That's 6 times 35 is $210,000. And then just to finish up the example here, the test costs, let's say roughly $1,500, and the repair cost of anything that we might repair is about $5,000. That's to maybe repair a termination at the time of the test. And I might be high with some of the numbers, but I want to show these numbers so that you can see how the life extension program works. So let's start at assessment 1. Here we can see assessment 1. It's now marked in green. That means if we look in the table, the asset's $35,000. The test costs $1,500. Therefore, you've saved $33,500 immediately. All you've spent on this particular asset that is defect-free is $1,500 to test it. The second assessment now comes back green, so we've got the same exact inputs in the table. We've saved $33,500, or we've saved about $67,000 with our second test. Now, in contrast, the third test, we see here it's in red. There's so many issues mid-span that this cable should most likely be replaced. And as we look at the cable, table, we can see assessment 3. Typically to replace it is $35,000. However, we did test it and we've got to replace it. That means we're negative $1,500 on this test right now if we're comparing to wholesale replacement. Test number 4, we believe that this should be repaired. So again, we've got the $1,500 to test it, identify where the issues are. We've repaired it for $5,000. So now we have a net savings here over wholesale replacement of $28,500. The next cable passes exactly the same we can see in number 5. The next cable fails. We look at the table, and it's exactly the same as the assessment number 3 that failed, that were negative $1,500. But if we add everything up right here, wholesale replacement would have cost us $210,000. We spent approximately $9,000 on tests for this day. We had one cable that needed replacing in assessment 4, and we had one cable that needed repairing at $5,000. That's assessment 4, and then 2 cables that needed replacing. So all in all, we spent $70,000 plus $5,000, that's $75,000, plus the 9 to test it, about $84,000. So what's actually happened here is we've got the whole loop back to a defect-free condition. We've only spent $84,000 versus $210,000. So we've actually extended budget reach right now for this loop by 2.5 times, which means we can go and assess another 1.5 loops, and with the same budget that it would cost to test just the one loop. So we've got 2.5 loops basically in all. So we've saved $126,000. And that's actually given us a return of $14 for every dollar that was invested, since 9 into 126 goes about 14 times. So this is what we're talking about in terms of the economics. But think about everything else that we've also done here. We're actually doing more with less. So project management, there's efficiency here. You're only replacing 2 cables and repairing 1, whereas a wholesale replacement approach would have taken would have required to replace all 6 cables. So there's project management. You're gonna finish a project quicker, 2.5 times quicker. Resource utilization. If a utility can bore in just a certain amount of cable per day, then in this particular case, in the proactive solution, you're only boring in 2 cables versus 6. So we're saving time with crew days and crew costs. We've got the investment return there, $14 for every dollar invested. But the main thing that's going to happen here is because we've got the same result, a defect-free cable system, we're going to improve the reliability of the whole system. So now let's look at risk assessment and rehabilitation priority. So now we've got all the results, and as Charles was showing, that we have the results that can be uploaded into your systems, your asset management systems. We talked about having the complete picture. We then talked about risk and health assessment, which is what we're getting into now, and asset condition. So what the structure information look like. We can actually look at leaking bushings, at transformers, and report them, as I mentioned before, if the arrest is in place. If it's not there, then maybe it should be put in there. But basically, we're looking at risk of failure, and also the probability of failure. So if the probability of failure, risk is the probability of failure multiplied by the impact of failure. This means that the total amount of risk exposure is the probability of, let's say, the fault occurring multiplied by the potential impact or the damage incurred by the event. And that impact could be financial in terms of customer interruption costs. You certainly got replacement decisions, and you've probably got some collateral damage costs that are financial. We talked about reliability indices, safety, SAIDI, CAIDI, CMI. That's all gets affected, and that has an impact to the utility. We talked about criticality. Sorry, I can't say it. Hospitals, major venues, data centers, petrochemical plants, airports. There's a big impact of failure if a cable fails and takes them out. And then also environmental. We've certainly heard a lot about fire risks, and we've heard about environmental oil leaks and the like. So we're looking at probability times impact as we look at risk. And we can model that in a rudimentary type of way, whereas as we look at the y-axis here, this is that probability or likelihood of failure. This is that risk that we talked about, where we can see here in the bottom left-hand side, we've got like a low probability and a low risk, a low risk of failure. So how do we determine this risk? Well, as we look at the top row here along the x-axis, we can see what might constitute a cable with a high risk of failure. Remember, we're looking at defects. Well, a poor neutral could contribute to it. We could see a partial discharge defect at operating voltage, or the cable could have been so close to failure that it could have faulted under test. So these are what we would call very high risk or very high probability or likelihood of failure type cables. And as we look at the next row, we might see joint and termination defects at operating voltage. Now, these types of defects, the components versus the insulation, the cable insulation, the components are usually much more resilient. So they still have a high risk of failure, but not as high as if the issue was in the insulation itself. So these may require, these are high risk of failure, so they should probably be looked at within the next, month or so, months to 3 months. Then medium risk, defects above operating voltage, or low risk, those are those passing cable systems where possibly the arrestor wasn't in place. So we're not clipping any of those transients that are out there, such as light and transients or switching events and the like. So that's looking at that risk of failure, the likelihood of failure. But as we look along the x-axis here, we can see an impact of failure. So this is that this is what we're talking about in terms of 2 cables could have exactly the same issues, but one, as we look at the top right of this particular matrix, one feeds a trendy downtown neighborhood. So there's an impact of customer minutes interrupted, whereas to the other end, again, it's the same issue. but it's less impact. It's maybe a parking lot in a rural area somewhere. So again, same risk of failure, but not the same impact of failure. So this is what we want to do, is work with you in terms of that improvement, by working with you on how to determine how you would rehabilitate your cable systems and the like. And let's move on, so that we can basically give you the precise condition of all the assets. We can give it to you on a loop by loop basis, ensure that the system is defect free, extend the life of aged assets, increase budget reach, reduce failures, and make sure that it's faster than replacement. So your expected outcomes are going to be increased uptime, decreased maintenance costs. You're going to have you're going to improve your capital reach, as we showed in the example, 2.5 times. Improve resource utilization, that your crews and crew days required to replace only those cables that require that require some form of rehabilitation. Only those are touched. So you're actually improving resource utilization. And then looking at the impact model, you know where to send those crews first, based on risk and impact of failure. So looking to extend the life of your cable system. So why choose MEGGER as the service provider? So we have over 130 years of experience in the electrical testing industry. And that means we've been in the industry for a long time. We're a proven leader. And we already work side by side with probably most every person that's on the phone, or every company that's on the call today. We also have premier test equipment. So they provide thorough and exhaustive diagnostic analysis of the assets, allowing us to find the defects in your cable systems that maybe others can't. And we also have OEM knowledge. You know, we manufacture this equipment. We actually sell the equipment, and not just service. So we're able to get more out of our test units and provide better and maybe more reliable asset management results. So you truly are partnering with a proven leader. So this, I believe, is my last slide. I just wanted to stimulate some gray matter as we go into a question and answer session right now. When you think about your program, what are you looking to do? What's the precise definition of the problem that you're hoping to address? Is it extend the life of aged assets? Is it commissioning new installs? Is it a little of both? Do you know your scope? What your problem scope is? Is it 1,000 miles? Is it just 50 miles? How are you currently dealing with the issue? Are you currently dealing with it? Are you running a run to failure approach? Or do you have a budget? Do you know your failure rate? Do you know how fast you want to fix the problem? Do you have a reliability metric? And how are you going to define success? So these are some of the things that we need to work with you together on to make sure that we tailor your asset management solution to your needs and not just to the general needs. And with that, before we take questions here, we do have a website, which everyone will get a copy of this presentation.
So hello everyone, and I hope this webinar was useful for you. And we're ready to take your questions. If you have any, please drop them in the chat box. I would like to also remind you that all the recordings will be shared within the next 2 days. And if you would like to request an attendance certificate, please use the survey questions that's going to pop up once you close this WebEx window. Let me repeat in Arabic as well. لما تسكرون اللي هو شاشة الويبكس راح تظهر لكم استمارة عن طريقها ممكن انكم تطلبون شهادة حضور. الآن راح ناخذ أسئلتكم. مهندس محمد معاي؟
ايه نعم سوسن.
الكويستشن الأول يقول the periodical maintenance of the paper insulated lead covered cable to avoid any problem, and the importance of the cable earthing. أظن هذا السؤال.
Thanks, Susan. Regarding the question, when it comes to PILC cables, the approach would be similar to XLPE cables and similar to what was described in the webinar specifically. So the testing that can be done is VLF tests, partial discharge test, and tangent tests. And of course, there would be some difference in the assessment in paper cables than in XLPE. For example, the tan delta test will represent the cellulose degradations because it's a paper cable, obviously, whereas in XLPE type of cables, it will represent more of the water-free content in the insulation. And similarly, in the partial discharge test, there will be some differences because normally PILC installations can handle more PD activity. So it will have a more tolerant PD assessment than the XLPE cables. And when it comes to earthing cables, of course, it's important. Earthing is important overall in all the assets that are present in the grid, because without it, it would be hazardous conditions. There might be step voltage that happens if there is any fault or failure in the insulation, and the step voltage can be fatal. And also for the protection system and having earth faults and the protection systems to act if there is any such faults. Without such system, it would be difficult to detect such fault.
Okay, so the second question is, how does AI and machine learning will be implemented in TNC?
For that, actually, it's, let us say, a stage after the testing and diagnostics stage. It's more of a software role, and there are plenty of asset management software, such as the IPS asset management software, where the data and the results of the testing that is done on the cable are fed into such system and such software, and the results based on machine learning can be obtained, and more analysis is done, like purely based on software.
Second question is, can you tell us about the TDR test and what is the importance of it?
Well, I believe this is a bit of a broad subject. The TDR test is one of the main technologies when it comes to doing testing on cables, and it's mainly like mostly implemented when it comes to cable faultification. And I think one of our seminars, the next seminar, will be dedicated to TDR mainly. So I would say stay tuned. Unless you have a very detailed question, you can send an email and we can reply to you accordingly.
Okay, another question is there any equipment to scan the buried cables and put it in BIM 3D?
Like we have only cable root tracers and that can indicate the location of the cable and the depth, but in our scope there isn't a thing that would make a full scan on the cable. Like if you imagine something like an X-ray scan or such.
Okay, so another question is, in medium voltage, are there Are there required sheets tests for the cable before termination, both end of the cable?
Yes, actually, sheath testings is one of the very good tests that should be encouraged to be done, especially in new installations, I would say, because simply having a good sheath means having less likelihood of any ingression of moisture or any types of contamination into the cable and eventually into the insulation, causing to elong its lifespan without any degrading effects.
What is the distance of tracer cables from MV cables?
I'm sorry, I don't think the question is very clear. I'm not sure I understand the question.
I think recommended distance for the tracer cable. Yeah.
So again, I don't understand, but generally speaking, the principle of cable tracing is that an audio frequency signal is injected into the cable, and you can detect it via a receiver. And the closer you are to the cable, the higher the signal.
If this doesn't answer your question, please go to the survey questions that's going to come up after this webinar has finished. And please ask your question and we will get back to you as soon as possible. Okay, so what is the recommendation for replacing the hotspot portion of cable? I mean, either exact portion or the whole? That's the question.
So that would depend on the outcome of the results. Like, if, for example, if you are having a cable that is tested and there is only the hotspot, as you refer to it, in one of the splices, so the best thing is to replace the cable portion only at that part. In other cases where there are multiple weak spots in the cable, it wouldn't be any longer economical to do such testing. So it's more of an economical point of view to take that decision. Like if there are, for example, many weak spots in the cable and you're having a high tan delta reading, it will be a better decision to do a whole replacement. Like the example we have seen in the webinar. And in other cases where there is one or two weak spots in a long span of cable, you can do that instead of replacing all of the cable span, and that would be a better option. So there isn't a single answer to your question. So it depends ultimately on the results that you would be obtaining from the test.
So, Mr. Muhammad, someone's asking for the industry standards so they could refer to it for this test. Where can they find it?
There are standards that mention, like the IEEE 400.2, that mention the tan delta testing procedures, and there are multiple standards in IEC, IEEE that mention the VLF test standards. When it comes to the PD testing, you have the general standards and PD testings, like the IEC 60-70, where describe the PD testing, but there isn't any fixed criteria to differentiate the condition of and assess the cable. So it's mainly based on experience and based on the tolerance, your tolerance to the grid and cable health. But for sure, please do drop an email querying these questions, and I can refer to you the proper standards for it.
So thank you, Mr. Mohammed. We have no further questions. And thank you everyone for attending today's session. Please be reminded that all recordings will be shared within the next 2 days. You can request an attendance certificate using the survey window that's going to appear once you close this webinar. And I hope to see you all soon again in our next webinars. And thank you all for attending. Thank you.
Thank you, Sosa. Thanks everyone for attending.